Well, good morning, everybody. This is the ABA Engineering Academy, and this is our June meeting for our webinars that we hold each month. And we're waiting on our special guest to get on. He had to reboot his computer. But while we're waiting, we want to bring up to date a couple of things here. This program is actually produced by the ABA Engineering Academy with the assistance of the ABA Broadcasters Association, along with the Georgia and the South Carolina Broadcast Association, help us in putting this thing together as well. Our co-host, John George, I don't think is with us this morning. John is at a transmitter site, and he said he would probably have very limited email capability or internet capability, so I don't think he made it on with us yet. So while we're waiting on our special guest to join us, he had to reboot his computer. A reminder also that we are sponsored by the Max Connect group. Now, this is actually used to be Bond Broadcasting, and they've reorganized everything, and now it's called the Max Connect group. And you can see the email address there on the website. And so just check that out and see all the different activities that he has going on. He's a full service engineering company, sales and service, all the way, everything from a microphone all the way to the antenna, and they do service work as well. A couple of other things that I'll fill in with here while we're waiting. The FCC has actually issued two deadlines coming up very, very soon, and I want to make sure that all the engineers are aware of that. And one of them is the concerning the EAS national test. Now, you know that's coming up on August the 11th at 2:20 p.m. Eastern time. And so that will be fed this year. It'll actually be through the PEP system, through your legacy EAS monitoring systems that you have. And so it will not be available on iPaws. And the reason I bring this up, make sure that you check your EAS equipment and make sure you have both of your monitor systems working, and they are the correct monitor sources that are assigned by your state EAS committee. Not only make sure it's the right one, but make sure that the actual audio is clean. And we've quite often we find out that even though they're monitoring the right source, it's got noise, a weak signal, or something like that. So make sure that it's got a good signal. Well, that will be at 2:20 p.m. Eastern Daylight Time on August the 11th. Now, prior to that, as most of you realize, prior to that, you have to re-register with the ETRS system on the FCC webpage, and that's required by July the 6th. So make sure that if you're doing it, that you get online and go through. Now, the neat thing about the ETRS system is that most of the stuff, when you go on to re-register, will self-populate itself. As soon as you put in your facility ID, most all the information is stored in the FCC system, and it will come up and be available for you there. Maybe one or two of items are not available, which is your EAS type of EAS equipment, and also the firmware that you're using. And one other date that I'll share with you, I see our special guest has popped on, so he got his computer rebooted. One other deadline here on July 13th, that is the deadline for all television translators and LPTV that are still analog. The cutoff date is you have to be have your digital system up and running by July 13th, or at least have an extension to do the construction permit. If you don't have an extension and you're not ready by July 13th, the commission will delete your license at that time. And I went on the website yesterday, and there's a large number of LPTVs and TV translators that are listed that are not ready. So make sure that you check into that. So I see our special guest is Sir Jeff Welton, and I think I added that because I know you've been sort of tied up there in the in the up in the Canada, they won't let you out anymore. So, but I'm glad to get you with us today. Jeff, I asked Jeff that he would come on and be with us today because of the actual. We're going into the summertime now, and there are a lot of lightning storms coming up, and Jeff sort of got some really good tricks and tips and all about proper grounding. So, Jeff, I'm going to turn the program over to you now.
All right. Well, and I'm going to tell you, so in addition to having to reboot the computer to get in here today, for the first time in a year and a half of doing Zooms and web everything, I've managed to stack two back to back. So at quarter two, I'm going to be out of here like a shot, just to give you the advance notification. Now, that said, let's whip through this. Most of y'all have seen some of this before. Some of it all have seen all of it. The concepts don't change a whole lot. And anybody who's familiar with the Motorola R56 standard, this will be a review of some of that. But I'm going to look specifically at stuff related to transmitter sites. So we're going to talk about the stuff that's out of sight, out of mind, because of course you get to the transmitter site, the grounds are all buried or they're behind a bunch of other stuff and you just can't see them. So we're going to try and hit a little bit of everything. This is a time-lapse photo of Tucson a couple of years back. So we'll talk about planning new sites, but even more important, we'll talk about what we can do with existing sites and when you got too much grounding, because surprisingly enough, too much can be just as big a problem, if not a bigger problem, than not enough grounding. Anybody that knows me knows that I have to talk about ferrites, and by all means, if y'all want to interrupt or type something in the chat, I don't promise I'll see the chat, but if you yell at me, then I'll absolutely hear that. So pipe in if there's anything at all that I hit. And we'll talk a little bit about other site related stuff, cooling, cleaning, safety. My short description for the perfect transmitter facility: if you keep it cool, keep it clean, and keep it well grounded, even a less well designed transmitter is going to give you some pretty good service. So that's the sort of thing we kind of look at here. The key to protection, is making sure that we conduct the strike pulse current to ground through a low impedance path. So what we're doing, anybody who's done any Ohm's law work with electronics, you're familiar with voltage dividers, okay? And we all know that current will flow through the path of least resistance. So the goal is to make that path not our transmitter, or whatever else you've got at the site, processors, remote control gear, antenna switches, tower lighting controllers, all that stuff. So if we can route the current around that stuff and not through that stuff, it'll save us a whole lot of grief in the long run and a few calls to the insurance company or just bucks out of pocket. The thing we got to look at is what we're dealing with. And lightning is intriguing because it carries components of almost every frequency that we're trying to pass. So we've got systems designed to pass audio, designed to pass RF at various frequencies from AM all the way up to the gigahertz if you're talking Wi-Fi bridges. All this stuff is going to be in a lightning strike to some extent. You've got a very fast rise time, about 0.2 microseconds, so that drops it right smack into the AM band. You've got a slow decay time around about 40 plus microseconds, so you're into the audio range. You're going to have a ripple on it as it causes any tune circuit it encounters to ring at its tune frequency. So again, the frequencies were designed to pass. And there are high frequency components. Now, I've seen some recent presentations from some folks that emphasize protection for the really high frequencies, like 10 megahertz and up. And I've read a lot of papers that say that the bulk of the energy is in the 1 megahertz or lower, that it decays linearly from 10 kilohertz to 1 megahertz and then exponentially above 10 meg. So I'm not going to focus a lot on the really high frequency stuff, but be aware there is enough high frequency component that we look at skin effect. So the surface area of your grounding conductors is probably as critical as anything. And that's why I'll push strap over wire for grounding any day, because a 4-aught wire's got about the same surface area as a 2-inch strap. Okay, just as one example. And the 2-inch strap's a whole lot cheaper than 4-aught cable. So that's something else to remember. Okay, a lot of strikes get pretty darn big, and they transfer a massive amount of energy. And this is so lightning protection is a multi-step process. It's not just the grounding. The grounding gets the surge from the antenna down to the earth. But what happens when that massive surge of current hits Earth with Earth resistance, and Earth has a finite resistance? So if you got a resistance of say 2 ohms per foot in moderately sandy or dry clay type soil, 2 ohms per foot, if you run 100,000 amps of current through it, then all of a sudden you've got 200,000 volts developing across that foot of earth, which is why they tell you don't stand with your feet apart in a lightning storm. Put your feet together, cut down the voltage from one leg to the other. That way we don't have to end up singing any songs at the end of the day. Now, the other thing that is important for this is MOVs. MOVs are basically a voltage clamp. All right. So if you exceed the voltage rating of an MOV, it will clamp and short circuit, and then it'll pass whatever current is hitting up against it right straight through. This is how we discharge a surge from the power lines to ground. So, if you catch a strike on the power lines, it comes in and the voltage comes in at a 1,000 volt strike or 2,000 volt peak, whatever, and you've got a 250 volt MOV, that MOV will clamp and send that energy straight to ground, and that's wonderful. But what if lightning hits your tower and a couple of 100,000 amps comes riding down the tower and hits Earth and spikes ground potential high? Now remember, in the example I just said, 100,000 amp strike, 2 ohms per foot on your ground resistance, so you got 200,000 volts right there just immediately. So at that point, we're way above our AC. So if we've got a really low impedance path to our surge protector from the tower with a strap or whatever have you, then that way we can run through the surge protector and dissipate that energy out on the millions of wires of cable and grounding that the power company so graciously provides. And that's really kind of the goal here. It's a two-way street, bidirectional devices. The other thing about MOVs is they do need to be fused, because when they fail, 100% of the time they fail short circuit. Now, if anybody's ever seen those little ceramic disc MOVs that the transformer manufacturers like to put across the transformer, and after a good storm, you go out and you'll see two legs and a little puff of soot in between them. Because MOVs that aren't fused, once they fail short circuit, will fail open circuit really dramatically. And if you're talking the big ones that we use in AC power protection, like the ray caps, the polyphasers, the LEAs, any of those good surge protectors, then when those fail, it's a dramatic explosion. It's a whole lot of fun to not be in the room for, but to see after the effect. So absolutely, any MOV device should be fused. Down to little ones cross transformer, not so much. And those are kind of really there more as a feel good. They don't do a whole lot because the transformer is going to dissipate a fair bit of energy anyway. So again, like I said, the half amplitude on the decay time, we're at the upper end of the audio band. Fast rise time, slow decay. This graphic, I've had this in here for as long as I've been doing this presentation, 25 years now, give or take. And it's a short, simple picture that basically says the taller it is, the more likely it is to get struck by lightning. So it doesn't matter what your lightning density is in the area you live in. If you got the tall stick, then odds are it's going to get hit by lightning more than the shorter stick half a mile away. Again, that doesn't mean 100% of the time, as you can see, but yep, the taller sticks get harder. So how much do we spend on lightning protection? And a lot of that depends. I mean, I'm not going to invest $500,000 to protect a $5,000 transmitter. That'd be foolish. Now, if I've got a couple of $100,000 worth of TV transmission gear, then yeah, maybe I would, because you only have to replace that once or twice before it gets really, really expensive. You also look at the revenue, a big billing station, you're going to tend to invest more. I mean, this is all ROI stuff that's pretty easy to figure out. And probability of getting hit by lightning down in the deep south, y'all got a much better chance than I do up here in the frozen tundra. For us, we had a storm last week. It was the first one we've seen this year, and we may have another one this summer at some point. But that's again, I probably spend a lot less on my station on lightning protection. It's still pretty well grounded because, well, I'm also a big believer in Murphy's Law. If you don't protect against it, that's when you'll need to be protected against it. So absolutely pay attention to that. As you can see, down Florida, the deep south through the panhandle and the Gulf states, that's where you're going to tend to see the most. So that's where you're going to tend to invest a little more care and caution into your grounding or your surge protection. So what I said earlier, you can have too many grounds. And a lot of folks come to me and they ask questions about halo grounds. And, you get these cell company buildings and they're beautiful. And they'll have the ring around the top and there'll be a couple of drop leads coming down and the rack's grounded and the or the conduits are grounded, the door frame's grounded, everything's beautiful. The challenge to it, and this is where you have to pay extra attention, is that it's really easy to lose sight of what we call single point grounding. You want one ground per item so you don't have any loops. And you do not want to daisy chain anything because that way you've got an input and an output on a piece of equipment, basically. You just made it a path for current flow. So ideally, each equipment would have one ground connection going to one common point in the facility. Now, the Halo grounds can be configured that way really easily because, again, there's a lot of things to choose from. But again, you have to be really careful to map it out and pay attention. The other thing you definitely don't want to do, ideally, in a Halo ground is those 4 drop leads at the corners. Don't run all 4 of them outside to a ground rod. If you do that, once again, you've created so many different paths, you've lost control of where the current flows. And remember, we're not going to stop lightning. Anybody who tells you they can prevent a lightning strike, I hesitate. I'd have to see some serious science before I'd believe that, and I haven't yet. Now, having said that, again, it's voltage divider theory. If I give you a half ohm path to a discharge location, and I give you a 50 ohm path to the same point, then the vast majority, 95%, 99% of my energy-ish is going to go through the lower impedance path. At that point, my gear with the higher impedance path has got a chance to live. So that's what I need to do. Now, the bottom line on this slide says use a tree, and I don't mean, the big oaks or anything. What I'm saying is, like, okay, say a studio facility. Okay, you've got multiple controller production rooms. So what you may do is establish a ground for each production room. So each room has its own central ground point, and each piece of equipment ties to that ground with a single run. Then you'll run each production room together with a single run to the facility ground. So you basically, like I say, a tree. But again, it's single point grounding, it's a star grounding configuration. Everything comes back to the one common point. Now, the big deal here also is that, and we'll get to it again in a little bit, that common point needs to be tied through an MOV type surge protector, or silicon avalanche diodes will work too, but any kind of shunt type surge protector between the ground and the AC entrance. And that will give you your bidirectional path that'll keep you from blowing up switching supplies every time lightning hits the tower or the AC lines. And for what it's worth, I would hazard a guess, and this is a guess, it hasn't been proven, but my theory at the moment is that most of the switching supply damage we've seen over the years has been because of tower strikes, not because of AC line surges. So just, file that away for future reference. So again, ground everything, coax shields, every piece of equipment. The big thing, then you'll notice this on just about every picture I have, there'll be something wrong. Ideally, you keep your grounds as short and straight as you can. No loops, no U-turns if you can avoid them, which is what you see here. Okay, the advantage to that is just maintaining a path. But the other thing, everybody says lightning doesn't like to go around corners, and that's true enough. But more to the point, lightning, well, every inch of wire you add is a little bit of resistance you've added. And again, we're fighting the battle of lowest possible path to ground. lowest resistance path. So again, here you see a couple of U-turns. You see, and it's hard to tell, but on the right-hand side, you see a ground wire coming down out of a conduit. Now, I don't know if we got any hams. I see one or two folks in the audience that I know are ham radio operators. And anybody who's ever wound a piece of wire through a ferrite choke just to make something to bleed off high frequencies, you make an inductor. You make something that is designed to slow to limit the current of any high frequency component. Well, if you run a wire through a ferrous or a metallic conduit, you've done the exact same thing. So you've just increased the impedance of that line to any higher frequency component. And as we said, lightning carries a lot of those. So if you are in a building where for whatever reason you've got a building inspector that insists that your ground wire has to be in a conduit rather than exposed on the wall, one of the things I recommend is use a non-ferrous conduit or a non-UPVC conduit as an example. Um, if you can't do that, then Romex, the spiral wound BX type conduit is probably the next best thing because the resistance of that casing is so high per foot that, again, it's going to be a whole lot better. Not ideal, but that's just one of the things that you kind of look at. One of the other things, if you've got a bus bar for your common point, and I'm a big fan of them because it gives you a convenient place to tie a bunch of things together. But if you do, make sure that you're using Nolox or some kind of antioxidant. You remember a lot of the older folks used to be that anytime Dad put a battery in the tractor, he always smeared Vaseline on the terminals just to keep them from oxidizing. But, and I mean, I doubt that that's probably a really good long-term solution, but in that particular case for us in the northern part of the world, it worked pretty well. So, something like that though, Nolox, Antiox, there's probably 5 different that I could come up with a Google search. But something to keep, because when you've got any kind of pressure connection where you've got 2 pieces of metal squeezed together, there's going to be air in there. You're not going to displace 100% of the air. And that means that there will be oxidation. And as you add oxidation, you increase resistance. So again, anything to keep them from oxidizing. If you've got to use a clamp connection, my preference is exothermic connections whenever I can, either welds, silver solder, silphos, brazing. I love CAD welding. I'm a huge fan of CAD welding. You get to blow stuff up on purpose. So stuff like that. One of the other things to pay attention to is make sure that your ground really is a ground. This is a building I got called to in Missouri. Turned out they were losing a lot of supplies in a 20 kilowatt. They were to the point where they were losing 5 or 6 a month. And at a couple of, well, I think those ones were 1,200 or so a piece. They were up there over $1,000 a pop. That stuff gets pretty expensive when you bought the transmitter because tubes were getting so pricey. So in this particular case, this is their primary ground for the facility. And as you can see, number one, it's running through a coax or a conduit. You can see on the right. But what you can't really see is that it's got a pressure clamp to a rebar. And as I said, not a fan of pressure clamps. I like to see exothermic welds where all the air is displaced. But in this particular case, what they're running to, they thought was a ground rod, was actually not a ground rod. It was the rebar used to hold the building onto the concrete pad. So it wasn't really a ground at all. We've run into similar situations, and I don't know if I've got a picture in this presentation, but if I do, you'll hear about it, where I had a transmitter grounded to a cold water pipe, except it wasn't a metal cold water pipe, it was a PVC cold water pipe. And plastic just doesn't seem to conduct that well. So those are the kind of things that'll get you. Okay, again, you've got a ground strap going to the transmitter. You've got a wire going through a conduit, so the wire's not doing a whole lot. Beyond that, the conduit is bolted to the chassis of the transmitter, so now you've created a ground loop. Now we'll take this one a step further. This is that same site in Missouri. So what happened here, like I said, they were losing a couple of power supplies, a couple a week at basically like 5 or 6 a month on average. We went down there went to the tower and started following the strap back and literally dug the strap back up all the way back to the building. Strap came from the base of the tower into the building, around to the back of the transmitter where you see it here, hooked onto this ground, which went through conduit all the way over to a surge protector. And then the surge protector ground went in conduit to that building J bolt that you saw earlier. So basically, what we had was a perfect path from the tower to the transmitter, and then nothing except the AC lines through all the switching supplies out to the power company's grounds. Now, it got even better because there was no ground rod out at the tower and there was no ground rod for the surge protectors. So the only path Lightning had, so it wasn't even a matter really of lowest possible impedance. The only path it had was through the transmitter to the power lines. So we put a ground rod out by the tower, and in Missouri clay, that involves a trip to Home Depot for a hammer drill attachment. And then we fixed the ground rod at the AC entrance, tied the surge protector to that directly, got rid of the conduit here, and rerouted a strap around the building to tie the two ground rods together. Because again, Earth has an impedance, and if you get two ground rods 20 feet apart, they're not going to be at the same potential on a lightning strike to the tower. So definitely tie them together with something that's got a fraction of an ohm per foot, like 4-inch, 2-inch strap, something like that. Even a heavy gauge cable in that case. And that's what we ended up doing. They went from several power supply failures a month to they lost one power supply over the next 5 or 10 years, and I think they've lost one since. So two power supplies over every 6 years compared to six power supplies every month. That's not too bad. So that's the kind of thing that you really need to pay attention to. The other thing is you can have the best grounding in the building ever, but if copper thieves have cut your wire or the strap where it comes out of the building, or in this case, it was soldered onto a wire and the wire was cut off, then you're not going to see anything. You don't get a whole lot of benefit if your ground doesn't connect to ground. Okay. By the same token, this one actually had a ground rod, but the ground rod was 2 feet long and driven at an angle, and it didn't even get into the dirt, let alone down to the water table or, anywhere where there was an actual ground reference point. So, yeah, again, make sure that your ground is ground. It's probably one of the biggest challenges we see because, of course, grounds are typically buried. So it does involve some shovel work in a lot of cases. In some cases, if you're up high on a mountain, whatever, you may need to put in a chemically augmented system, chem rods or whatever, and they work well. One of the other things in an extreme case, I saw one in Arkansas where they kept losing stuff and losing stuff. They actually drilled a well and used the well casing as their ground point. So again, that's a high price solution, but if you're losing, several thousands of dollars a year to lightning damage, sometimes you take the higher price solutions. This particular one didn't have a surge protector. Lightning hit the tower, had nowhere to go except through the transmitter power supply, and quite literally blew the transformer. Well, transformer power supply blew a whole bunch of stuff out the side. Now we replaced that transmitter with one of ours, and that's wonderful for us. But if we hadn't gone through at the same time and changed the grounding, it just would have been the same thing all over again a couple of months later. All right. So don't assume, that I'll cover this so mother doesn't hear me, but don't assume that just because you bought a shiny new transmitter that it's not going to blow up on a lightning strike if you've got the same ground issues that cause your tube rig to blow. So definitely these are the kind of things we like to address. Okay. Again, with the metallic conduit, you notice I've kind of got a theme going with that, but absolutely you need a surge protector. Whether it's this one was one we used to make. We outsource ours now to a company called Raycap. So Raycap, Raycap, you can get them from us, or you can get them probably cheaper from Raycap directly or any other reseller. Polyphaser I think is still around. Control Concepts, uh, let's see, a lot of the other ones. Polyphaser is bought LEA, and there's another one I can't remember. So anyway, point being, MOV type or silicon avalanche diode type surge protectors are definitely critical, because that's the thing that connects the ground to the AC lines. So you have a path between the two that isn't through your equipment. Okay. And that's the thing to remember. And again, don't care what brand you use, shunt type MOV protector with fused links. By the way, if you have a fuse fail, replacing a 40 amp cartridge type fuse with a 5/16 inch bolt, even though the bolt will fit, not recommended. And yes, we have seen that. So part three of your lightning protection is the ferrites. And the ferrites, like I said, the problem is everybody's heard me talk, here's ferrite, 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 to the point that they sometimes miss the overall message. Ferrites on their own don't do a whole lot. Remember that the theme of this whole discussion has been voltage divider theory. So what the ferrite can do in a properly laid out system with good ground and decent surge protector is the ferrite will give you that little bit extra impedance on your equipment to make the alternate path through the surge protector look even a little more desirable. Okay, again, on its own, the ferrite's not going to stop lightning. In fact, the ferrite will probably explode on the first lightning strike, and that'll be your cue that you need to fix some other stuff. So how they work with a ferrite, when you've got a feed and a return, and if you're looking at my camera instead of the slide, you'll see I do a lot of hand gestures for this. I'm not Italian, but for this particular display, you'd think I was. Uh, so you got a feed and a return, you put the ferrite around, and what happens if one of them gets a surge, a common mode surge, it will attempt to induce an equal surge into the other conductor. Now, when that happens, the advantage is that the potential difference between them stays the same, and that reduces the chance of blowing up components. Now, that's an extremely oversimplified explanation. And if you look up, if you hit Google for permeability or ferrite, either of the two, that or both, then you'll find a lot of really good explanations of the science. But essentially, the ferrite is a iron or some ferrous material with carbon and epoxy to hold it all together. Depending on the ratio of ferrous material to carbon will determine the composition, the material number. We use a lot of J material and 43 material over the years. I think everything we do now is 43 material. And you can see the different permeability characteristics, where it will saturate, at what frequency. Now for lightning protection, because we're looking at common mode protection, so where the feed and the return are equal, nothing happens. The ferrite's inert. So at that point, it could cut off at 1 hertz. It wouldn't matter. That's a gross exaggeration, but you see the point. So definitely you want the most ferrous or lowest permeability you can get in the ferrite. So now I'm going to quantify that a little too, because if you're putting it on power supply wiring and you have a floating supply, then you're going to run each inductor through a ferrite instead of running all the inductors through the ferrite. And we'll talk about that in a little bit, a couple of slides down. But those are pretty rare in our line of work. Almost everything we do, the supply is referenced to ground, unless you got a modulation transformer that's shorted to the case and it's sitting up on 2x4s, in which case you got more problems than anything we're going to solve today. But and don't lean on it. So yeah, there's safety tip number one. If you walk into a site with a tube transmitter and one of the transformers is on 2x4s, don't touch it. All right, moving on. So where do we put the ferrites? Anywhere where I have a feed and a return. So coax cable is the number one, and AC cabling. So now AC, if I've got split phase 240, or if I've got three phase, then I've got more than one feed, but I've still only got one return. So I'll run all three feeds and the return through a single ferrite. So just one toroid around the whole issue. If I've got enough slack in the cable and the ferrite's big enough diameter, I may take a loop through and basically make an inductor and run them through again. By the same token, on the RF lines, a lot of folks have seen the loop at the base of an AM tower, which adds a little inductance. I'm, again, it's a matter of degree. Every little bit of inductance we can add to where we don't want the lightning to go will help it to jump the spark gap and head to ground and go where we do want it to go. But it's all a game of, I guess, a game of inches. We do a little bit at a time wherever we can. Now, one of the other things, if you are running an AM and you put a ferrite on a coax and it goes above ambient temperature, it gets warm. That means it's saturating, which means you have an imbalanced current. You don't have the same feed and return currents in that particular cable. Usually that means you've got a ground loop, and it's a great troubleshooting tool for AMs, because if I put one on the output of the transmitter and it gets hot, loops probably between the phaser and the transmitter. If I go to the output of the phaser to the various towers, if two are cool and one is hot, that, then I know I need to look for a bad ground. Maybe I don't have a good ground connection. Maybe the ground strap is busted. Maybe it was stolen. We ran into one where the transmitter was, and out here, all our grounds are run above ground because we hit bedrock pretty much at as soon as you get through the topsoil. So a lot of times the grounds are run on the surface. And that well, these days, not so much. We don't have a lot of AMs, but the radios used to all be laid on the surface as well. And so we had one where the AM was tripping with SWR, and they called us, and I said, yeah, dude, everything looks good. But we put it in the dummy load and it came up just fine. Transmitters, nothing wrong with it. So they got out and they started looking, and they found somebody had started to cut through the primary strap from the phaser close to a quarter mile away to the transmitter. And they got all except the last inch through, which was when all the current took over and blew the strap apart, and they found a set of tin snips and a thumb. So anyway, it was easy to track that guy down. But point being that there is a lot of current flow through these, and you do want to pay attention to that as well. Okay. So ferrite on AC cabling, again, all the feeds and the return through the ferrite, loop it if you can. Obviously on this one, you're not going to loop through that ferrite. It's not big enough, although they could have taken one of the ones off the coax feeds and run an extra turn through there. Again, it's a matter of degree, and it depends on your own specific situation. Okay. One of the other things, if you do have an AM and it's near the tower, you can run your radials over your building and create a Faraday cage, and that sort of brings you down below ground level. And that can cut down on a lot of lightning current in the building too, as far as that goes. Now, remembering that the radials themselves are not part of the lightning protection as far as the earthing system. They're a counterpoise for signal propagation. I see Mike Patton's here, and I know Mike knows more about this than I do, but so questions about that, certainly feel free to ring one of us up. All right. So, shielding everything is a really good idea. And this is, there's one, let's see, I'm going to skip ahead a couple of slides because there was one or two that I wanted to hit. That was the one. So ground rods was the other one. I get a lot of folks I've been to a lot of sites where you'll see ground rods everywhere. And I mean, I walked to a site, 10 by 10 site, and they had, they had a ground rod at each corner and two on each side. So basically the ground rods were 3-4 feet apart, and it doesn't hurt anything, but you're wasting an awful lot of money. Ground rods have what's called an electrode interface hemisphere. It's basically their effective radius. And the radius is nominally the length of the ground rod. So if you drive a 10-foot ground rod, then it's effective for a radius of about 10 feet from where it's driven. So I wouldn't need to drive another ground rod at that 10-foot mark. If I drove another 10-foot ground rod, I'd drive it 20 or 22 feet away. That way I get the most bang for the buck, if you will. Like I said, there's some theory that if you drive them too close together, that they can cause a diotic reaction that causes one to corrode away, and possibly in really acidic soil or alkali that might happen. But I haven't seen, again, a lot of science to support that. More to the point, you're just wasting money, because if you drive two ground rods, if I drive two ground rods, 10-foot rods a foot apart, basically I drove one 11-foot ground rod as far as the actual math works out. So, I just spent twice as much to do it, was all. So definitely, you don't need to put the rods that close together. And all means, if you've got the option, make your ground rod connections permanent, exothermic with silphos, braze, weld, whatever. I guess you're not welding to a ground rod. Maybe you could. I can't. But so just as a reference, a couple of years ago, I figured after all these years of talking about it, I should check out the ground at my own house. And it had a clamp connection with a stranded cable going through just a regular pressure clamp onto the rod. The downside with those is that oxygen is malleable. So as you put pressure on it, it will deform to displace air in the connection. And unless you've got the perfect crimp tool, you're not going to displace all of the air in any connector with a crimp connection, whether it's a wrenched on one like a ground rod or whether it's an actual crimp tool. I mean, the dies for the crimp tools we use are upwards of $2,000 a pop, and I don't see them a lot in the field. So you're much better off to silphos, silver solder, braze, or CAD weld your ground connections whenever you can. Obviously, you don't always have that choice, in which case, like if you got to go to a bus bar, then yeah, I would solder the lug onto the wire or the strap. Well, if it's a strap, you just drill a couple of holes, but make sure that you use the Nolox or the antioxidant in there as well. Okay. Um, Spark gaps, if you've got an AM, then the best thing to tell you about spark gaps is that the ones at the base of the tower are your primary defense. They're always set too far apart so they don't trip on rain and insects. So they're, from a lightning protection perspective, not ideal. You need to have a set at the output of the ATU, and that's including if you've got a skirt fed, because by the time you get to the ATU output on a skirt fed, you're not a ground potential by any stretch. So put a set of spark gaps there. These are made with carbon balls. Carbon balls, we get them from a company in California called Ross Engineering. About $250, you can roll your own set of ball gaps. And if you look at our Waves newsletter, our tips and tricks articles, you can find a way to build your own. I wrote an article about it several years back. So definitely a good thing to remember. You can calculate the gaps, set them. I use the hammer whack method. You set them until they just arc and then whack them until they just don't. So that's my highly sensitive and scientific method of adjusting ball gaps. Indoors are best if you can do it for preventing false trips. I wouldn't necessarily do it this way, but that photo, of course, goes back a bit. One other thing about grounding is ground guy wires before they hit the anchor, because when you run a lot of current through concrete, all the moisture in it expands and bad stuff happens. Okay, we're getting pretty close to my cutoff point. I've hit most of the grounding stuff. There was one other thing there. This is your typical transmitter site. So you've got AC coming in from the street, tower out behind in the back field, and you hang the transmitter in the middle so all the current can go through it. It's not ideal. So you can take that and modify it pretty quickly, electrically speaking, by hanging the transmitter off to the side, giving a surge protector to provide a path between the AC. And remember, the surge protector is bidirectional. So it's not just the tower strikes as shown here, but you will get the occasional power pole strike, and that can go to the ground at the base of the tower or your reference ground. And then the ferrites on the AC lines and the coax to the transmitter to raise the effective impedance of the transmitter and make it look like a less desirable path for the current to flow. Okay, so that is really right there. These two slides, more than anything, are what we want to accomplish. Okay, and if you do that, you'll be good to go. Yeah, like again, there's always stuff. I mean, I walked through one studio once in after a trade show. We had a discussion, and I gave them some thoughts of stuff to do, and they went and did it and cut their failure rate way down. But I've had other ones where you've had to go back 2 or 3 times. And let's say Mike Patton there, we first met at a site in Memphis where I think I'd been there twice, and one of my other guys was there, and Mike had been there, and we finally found that the power company ground coming off the pole was just stuck into the ground. It wasn't actually connected to a ground rod at all. It had been at one point, but I think it had just oxidized or corroded away. So that's the kind of thing that we want to look for when we do an inspection. One of our guys used to say that you pretend you're a lightning bolt, you start at your tower, you head back to the AC lines, and you look for every path between one and the other, and then just try to calculate the impedance in the process. So these slides talk about some of the things you can do to improve your overall configuration, rerouting coax, adding ferrites, things like that. So, these are the kind of things that we like to see more than anything at all. Ferrite, we discussed that ad infinitum. So ultimately, say, keep it grounded, move the air, keep things clean, and overall, things should be pretty reliable. On that note, I wrapped it right up to my deadline to head out. I can handle one or two quick questions if you got any, but let's rock them fast. Otherwise, thanks much.
Yeah, thank you, Jeff. That was really good and informative. And just for you folks that are actually in Alabama or in the Southeast, Jeff will be with us virtually, I think, unless he can make it out of Canada, at our ABA Engineering Academy, which is coming up on August 13th. So you can check our newsletter and we'll have more information about that. Thanks again, Jeff, for being with us, and we look to see hearing from you in August. Next month, and I think we still have him with us. Wayne Presida, I think, are you still with us? Oh, okay, I guess Wayne dropped off. Wayne
No,
Presida
I'm
will.
here.
Oh,
I'm here,
okay.
Larry.
Yeah,
Just
Wayne
took
will
me a
be.
minute to find my unmute.
Oh, okay, you're on mute. Okay, he will be with us next month on our Engineering Academy webinar. And if you want to just say a few words about your presentation, covering something that's really rampant in the country now, and that's cybersecurity.
Well, certainly that is a topic that seems to be one of those that we can't get past and get around. So we'll talk about cybersecurity, and certainly ransomware is an aspect that has become seemingly very popular these days. So hopefully we can look at some practical steps that can take to not necessarily eliminate, but minimize the impact.
Oh, that's good. I appreciate that, Wayne, and we look forward to having you with us next month. Another month, going a little bit later, Mike Patton, you still with us? Mike will be with us in August, and you might just give us a little outline of what you're going to be talking about in August.
Well, you'd asked me to talk about directional antennas for AMs. That they're not as widely used as they used to be. A lot of stations have been kind of abandoning them, but they've streamlined the rules quite a bit, and they're still relevant. We still see a number of directional antennas, and I'll be happy to discuss the care and feeding of a DA in this modern era.
Yeah, I've heard a lot of people say the new guys that are coming into the business now, they don't like AM and they despise directionals. So, and
well,
that's just
it was
because they
always a
don't.
bit of voodoo, but even voodoo is understandable. It's not absolutely magic. It's straightforward.
Yeah, and I
We'll
think you also talk about MOM a little bit.
Yes, that is an essential tool these days. It's not always applicable, but the FCC and the engineers who developed that tried to make it as widely applicable as possible. And we'll talk about the stations that are eligible for that and the ones that aren't, and the pros and cons. Not everybody chooses to go that route, but for the most part, it's a smart thing to do.
That's great. We look forward to having you with us in our August webinar.
Thank you.
Wayne will be with us in July, and Mike will be with us in August. And if you missed part of this one, or you would like to go back and watch it again, or share it with other people, we do archive all of our webinars on our YouTube site, and there you see the link to go to that, or you can just go to YouTube and search for the ABA Engineering Academy, and it'll bring up all of our videos. Once again, move on over to here. We thank everybody for being with us, and the information we shared with you before we actually started the program, having to do with EAS tests coming up in August, and more importantly, the re-registering with the FCC's ETRS site, the EAS test reporting system. That has to be done by July 6th. So if you don't, if you haven't done that yet, you need to, it is open because I actually went to it this morning and they do have it open and ready for you to go in there. And the neat thing about it, most of all of the information that it asks for you to re-register your station will self-populate as soon as you enter your facility ID. Now, I will share with you the ABA Engineering Academy is working on a tutorial, a video tutorial of how to actually go and walk through that site, and that should be up on the YouTube site probably sometime early part of next week. So uh, all that information will be available on our weekly newsletter. If you do not get our newsletter, Monday Morning Coffee and Technical Notes, just drop me an email there at that address, lwilkins@al-ba.com, and we'll be happy to put you on the mailing list for it. And we have all the information in there about the webinars and a lot of technical information, and we'll have some more information about registering your station on ETRS. Deadline again is July 6th for that. And one final note before we drop off, we do another newsletter we started a few months ago for pro audio people. We found out there's a lot of broadcast engineers that are involved in the pro audio arena, either live audio mixing or maybe even working in a recording studio. And so we started a new newsletter several months ago for the pro industry. So if you'd like to get on that mailing list as well, just drop us an email again at lwilkins@al-ba.com. So we thank everybody for joining us, and we'll see you next month on the ABA Engineering Academy's webinar series. Thank everybody for being with us.